Hello everyone and welcome to my YouTube channel in which we are studying and discovering different ways for having simulation and coding and specifically for vapor compression cycle, heat pump, HVAC and R. So let's continue and now we will go further deeper into the looping problem which we have done in the last video. So now we will try to improve our code and we will also add some important parameters like COP is one of the important parameter which we have already included in our previous video. But now I would also like to know how the compression ratio, the mass flow rate and the compressor discharge temperature, which are also key parameters when we are studying this vapor compression cycle. So how they also change as the evaporator temperature increases. So let's ask, please modify the code so that besides COP I also want compression ratio, mass flow rate and compressor discharge temperature plots with evaporator temperature. Please provide all these plots in one window. So we can easily analyze all these plots and we can compare these results together. Also provide the results in an Excel sheet. So now the Grok is working on the code and it's saying it is modifying the previous code, include additional plots for compression ratio, mass flow rate, compressor discharge temperature alongside COP, all plotted against evaporator saturation temperature from -10 to 20 degrees Celsius, and all four plots will be displayed in a single window using matplot library subplots. And the results: evaporator temperature, COP, compression ratio, mass flow rate, compressor work, condenser heat rejection, compressor discharge temperature, and state points will be saved in the Excel sheet. So here is our modified code and we can see like it is working on it and it is saving the results in the Excel sheet and plotting all the metrics like COP, compression ratio, mass flow rate, compressor discharge temperature, which we have asked it. So just copy and we will close the previous files and we will make another new Python file and we will name it Grok 5. Just paste this new code and just run it. Now we have run it again. Now it is run and seems like it has provided what we needed. So here you can see the first plot is the COP, different refrigerants with increasing evaporator temperature. So we can see, and we have discussed this plot in our previous video. So here is the compression ratio plot, and here you can see how with the evaporator temperature the compression ratio is decreasing. So the compression ratio, as you know, is the ratio of the pressures and condenser pressure divided by the evaporator pressure is the compression ratio. So as the temperature increases, you know, the temperature lift is decreasing, so is the compression ratio. So here you can see this R32 and R32 and R410A, they have similar compression ratio profiles, whereas the ammonia has the highest compression ratio. So here is the third plot where we can see the mass flow rates. So we can see there is very negligible difference in the mass flow rate of ammonia, which is the lowest, and there's no such change as the evaporator temperature changes. And here you can see with the R32 it decreases also very slightly, but it has more mass flow rate as compared to the ammonia, and the largest mass flow rate we can see is of R134A. So all these mass flow rates are actually declining, decreasing, but you can also see the rate of change of mass flow rate as the evaporator temperature is increasing. So it is also very interesting. The fourth plot is our evaporation saturation temperature with the compressor discharge temperature. So you know, like the compressor discharge temperature is also one of the very key parameter when we analyze vapor compression cycle, because we don't need higher discharge temperatures. So here the important thing you want to note is the highest discharge temperature is for the ammonia. So actually the natural components or hydrocarbons, they have higher discharge temperatures. So here we can see ammonia is also having 140 degrees Celsius. So it is the highest temperature, and as the evaporator temperature increases, this discharge temperature is decreasing. So all the refrigerants, their compressor discharge temperature will decrease because the temperature difference between the evaporator and the condenser is decreasing. So this is the desirable results, or these are the results which should be like. So here you can see that ammonia is not giving us a desirable result because it is giving us the highest discharge temperature. And why it is not a desirable, you know, like it affects the life of the compressor, and it affects the compressor lubrication. So the life of the compressor will decrease, and it sometimes also affects the compressor efficiencies. So here you can see all these four plots in one window, as we have given uh, command to grok. It has provided us what we want, and you can see ammonia has best COP, and R134A also has the same COP, so it's good. Here you can see the compression ratio is also higher, so that's not actually desirable. We need a lower compression ratio. The lower the compression ratio, the less work a compressor has to do. So here ammonia is not as much desirable. Here you can see R32 is desirable, and here you can see the mass flow rate, the minimum mass flow rate. So the minimum mass flow rate is for ammonia. The minimum mass flow rate also indicates that this refrigerant will has least charging amount in the circuit. And here you can see ammonia is also not desirable because it is having the largest discharge temperature. So here you can conclude there are some things in which ammonia is preferable, and there are others in which ammonia is not preferable. So this is the thing. Whenever we are going to select some refrigerants, there are different parameters which we have to monitor, not only the COP but also these things like discharge temperatures and mass flow rates and compression ratio. So these four things are the main parameter which we usually see for designing or for the selection or the initial screening of the refrigerants. So here you can see how easily we can just plot them and we can see them. With this, it has also saved the result in the VCC sheet. So let's see. So here you can see the Excel sheet, and let's see how it has saved the results in the Excel sheet. So here for our 134A, it has saved all the results: compressor, compression ratio, COP, mass flow rate, and compressor work, and also condenser heat rejection, compressor discharge temperatures, and for the different refrigerants, you can see it has saved it right there. So this is how easy you can just plot, and you can just see the performance of different refrigerants. And let's see, like if you want to change the name of the refrigerants, and instead of ammonia you want isobutane, which is usually used in the refrigerators. And for instance, I also want to see, instead of R32, let us say R404A, which is also very famous refrigerant. So let's see how it changes our results. So here you can see the results are now changed. So now isobutane, you can see, is giving us the highest COP values, and then R134A, and the compression ratio is also less than R134A, and the mass flow rate is also less than R134A, and the compressor discharge temperature is also less than R134A. So if we take R134A as a reference refrigerant here, and we want to compare or other refrigerants with it, we can see here it's very clear why isobutane is used in the refrigerators nowadays, because of its better properties: better COP, less discharge temperature, less mass flow rate, less charging, less compression ratio, and which less compression ratio causes less work and improves the COP. So here you can see how simply you can just compare different refrigerants, and you can screen them out if you are working on it. So thank you very much for watching this video, and if you like it, please like the video and subscribe my channel. And I have also uploaded the code in the description, so you can just download it and you can use it for your study or for your research work. Thank you very much.